Okay, couple of logistic notes. I hope that you are working on your homework. All of you should be on Gradescope, right? Have your homework. You should have been able to download the data sets and everything and go through the homework. Okay? Any sort of problems with respect to, if you have any problems with respect to the homework, send ping Piazza. In particular, ask Sarah, who is the head TA on Piazza, and she's handling, adding on Gradescope and stuff like that. Okay? So let's make sure that you have that. The assignment is going to be due in 1 week, so next Monday. So you should be, be able to work through the whole assignment by next Monday. You have TA office hours, so you basically have almost 4 hours this week to talk to TAs. So Mondays from 4 to 5 and Fridays to 1 to 2, Hubert, and then Diraj on Tuesdays from 4 to 6. Okay, so make sure that you talk to the TAs because TAs know the problem, they have the solution, so they know exactly what needs to be done. Okay. The other thing that I'm thinking about, something that I've done, I didn't do it last class, but I'm thinking of doing, is I'm thinking of giving everyone a 5-day budget that you can use throughout this course for your assignments. Okay? So 5-day budget basically means that, for your assignments or projects, you have, you can spread 5 days however you want to spread it. We'll keep the track of how late you are, but you can take up to 5 days. That's the maximum I'm willing to give, okay? So what that means is that if you don't want to turn in your assignment on Monday, you have 5 days, and then you have basically 0 days. But you can use those 5 days, you can use 2 days for this assignment, 1 day for the next assignment and so forth. TAs will just, on Gradescope, it's going to be recorded, okay? Anything beyond 5 days, you will get penalized. So I'll announce it on Piazza as well. Okay? Because I know some of you, like I'm receiving emails, people are saying, well, I have an interview on Monday, so I can't turn the assignment, so you can use that. But I can't give you more beyond 5 days because there are students who come over and say, well, I have a midterm on Friday that I need to study for. Can I get an extension for Monday's deadline, right? So again, you can use those 5 days, but generally make sure that you balance your time appropriately. In particular, for this assignment, I wouldn't use my budget, okay? So, particularly when it comes down to projects, your second and third assignment, you can use that. And especially try planning it beforehand. I know that there are some master students, some PhD students, some of you are probably on the job market and so forth. So make sure that you balance your time appropriately, okay? Any questions? Any questions about homework? Easy, hard? Yes?
Just a question with regards to the second assignment.
Yeah, so for the second assignment, you can reuse the code written for the first assignment, for sure. So you can reuse some of the tools that you're going to be building for your first assignment, yes. How many of you have started looking at the first assignment? Okay, good. Not all, but good. Make sure that if you haven't had experience with backpropagation algorithm and so forth, make sure that you start early, right? Okay. So there's going to be class on Wednesday. There was no class last Wednesday, but this Wednesday we will have a class. Okay, let me just start where we stopped last time. Initialization. Remember last time we quickly looked at initialization. We basically said that you can't initialize weights to be 0. Otherwise, the gradients would all be 0. You can't initialize weights to be the same value and so forth, right? So one good way of initializing is to just sample from uniform distribution using this equation where these hk minus y are the sizes of the layers, right? So you have a little bit of a balance. I think that someone asked on Piazza, whether we have to use this particular initialization. You don't have to. You can just sample from a Gaussian distribution with some small variance. That will work as well. Okay, particularly for the models that you're building. There was a few questions also about like a hidden layer. What does that mean? I think in your homework, when I say a one hidden layer neural network, that means that you have one hidden layer. Because sometimes people can count it differently. They think input is a layer. And you have a hidden layer. You have an output layer. So effectively, one hidden layer neural network is like 3 layers. But when I say hidden layers, I really mean the hidden layer. So whenever you're building a 2 hidden layer neural net, that means that you have to have 2 hidden layers. Right? You don't count the input layer and the output layer as additional layers. It depends on who you talk to and how people count. Model selection, again, we've covered this very quickly, but I just wanted to, again, point this, that you have a training set, you have a validation set, and you're going to be tuning your hyperparameters on the validation set, and then you're going to be estimating your generalization performance, reporting accuracy on the test set, right? And the goal is to really see the behavior of the model on unseen examples, previously unseen examples. Okay? Yes?
When we do K4 cross validation, should we set the validation set separately or?
So for this particular assignment, you don't have to do K4 cross validation. So in this particular case, you actually have training and validation set already predefined for you. If you wanted, yeah, so in general, what you tend to do, like if you wanted to use K4 cross validation here, what you would do is you would combine your training and your validation set into one set, then partition it. Let's say you're doing 5-fold cross validation, and then you would, take 4/5 as your training, 1/5 as your validation, and you just rotate it 4 times or 5 times, right? So you would actually build 5 different models, and your ultimate prediction would be to average over all of these 5 different models, right? Yes.
People actually do that in practice when the data sets are so big?
No, in practice, people don't do that. That's generally done whenever your data sets are small enough. Like in the case of examples where you don't have large data sets. Yeah.
And then for the hyperparameters, wondering if there's a particular order that you should tune them. For instance, with number of epochs, you might do like an early stopping thing. So the performance might be really bad if you went all the way and you set a hard 100 epochs. But then when you're training like learning or like hidden layer size or regularization weight, you usually typically train a bunch of models with one setting of that, and they've all been trained for the same number of epochs, right?
Yeah. So generally, when you're doing hyperparameter search, there isn't very good answer as to what order you should be fine-tuning those hyperparameters. Generally, people try, a few things, like either do grid search over a whole bunch of different hyperparameters, like learning rates and so forth. They typically run for more epochs to see overfitting. So there isn't really a good answer to say, like, first search for this hyperparameter, then this hyperparameter, then this. It's mostly based on, to some extent, it's intuition. The second is, you're just trying to explore depending on the problem that you're trying to solve. So there isn't really a good answer of how to tune hyperparameters. Most of the time, if you have access to multiple machines, you can just run things in parallel. The other question that I also want to address, I think somebody asked on Piazza, in the homework, you have to run for like 200 epochs, but maybe after 60 epochs, you see overfitting, right? So when I say run for 200 epochs on your homework, it doesn't really mean that you really have to run for 200 epochs. A lot of it really depends on your model size, what you're exploring, what your learning rates are, and so forth. So its judgment should be up to you. But the bad thing is when your training curve goes like this, and your validation curve goes like this, and you stop here, right? You say, well, 200 epochs, I'm done, right? So depending on what hyperparameters you're using, you should really, try to train for as long as possible up until you start seeing overfitting, right? Because it doesn't make any sense to stop at a particular point where you don't see overfitting. Like, for example, here, if this curve would continue going down and it would be here, would you stop here? No, you would continue training, right? So you really need to find a point where you start seeing overfitting, right? So that's why, again, the second part of your homework is really trying to get you to look at these curves and have a little bit better understanding how the training proceeds, right? Yes, maybe last question.
So all deep neural should have the capacity to overfit?
Yeah, generally we're going to come back to this point in today's lecture. Yep. Okay, so tricks. These are pretty useful tricks to know about. You'd want to normalize your data, particularly when you're working with real value data. For this homework, you're working on MNIST digits, so you don't really need to normalize because these are already normalized between 0 and 1. But in general, if you're working with some data sets, you would typically standardize your data set by subtracting the mean from each dimension. So just computing the mean and subtracting the mean. So basically, every single input would have 0 mean. And then you divide each dimension x by its training standard deviation, right? So you're kind of like saying, on average, each dimension should be 0 mean variance 1. And this can speed up training. Here's kind of a very useful trick to keep in mind. It's very primitive, but it works surprisingly well. You start with a large learning rate, 0.1, okay? Generally, whenever somebody asks you what learning rate you should be using, the answer is 0.1 or 0.01. Right? Two learning rates to use. Those are pretty good ones to use. And then you can start training it, you're maintaining until your validation stops improving, so it kind of saturates. And then you can divide the learning rate by 2 and look at your validation curve, right? Some of the most successful systems, you see the performance kind of like dropping down, and then it stabilizes. You divide the learning rate by 2, like goes down and stabilizes, divide by 2, and so forth. So this is, again, it's just a hyperparameter, and that's a pretty good trick. It doesn't work always, but it's a pretty good one to know about. Mini batch and momentum. So this is another pretty common thing to do. In many examples, whenever using stochastic gradient descent, instead of updating parameters after every single example, you'd actually would create a mini batch, right? A mini batch would typically contain 100 examples. Sometimes people go by the powers of 2. So it would contain 128 or 256 examples. And then you would average the gradient for that mini batch. So you basically, it's almost like you're computing the gradients for every single example, and you just average. And that can give you a more accurate estimate of the gradient, but you can also leverage matrix operations, particularly for GPU computation and CPUs as well. It's much easier to leverage matrix operation. In fact, when you're using GPUs, processing 128 examples versus processing 1 example is about the same, right, the speed-wise. So it makes sense to leverage that. Momentum is another very important point to use whenever you're training these models. And the way that it operates is that you're essentially using an exponential average of the previous gradients. Okay? So what does that mean? It basically means that whenever you compute gradient at time t, you're computing the gradient of your loss function, let's say on a mini batch, average over the number of training examples in your mini batch. And then you have this parameter beta times the previous gradient at time t minus 1, right? So it's at time t minus 1. Beta is the hyperparameter. 0.9, set it to 0.9, works pretty well. Or 0.8, depending on the problem. So what this is doing, this is essentially saying that if I compute the gradient and it's pointing in this direction, and at the next time step I compute the gradient and it's pointing in this direction, maybe you should be moving in this direction, right? So the idea is that whenever you have highly sort of high curvature, right? You know these examples where gradient descent methods typically fail. If you have a high curvature and you're sitting at the point, the gradient will point this way. You jump and the gradient is going to point this way, and then you jump and the gradient points this way, and so forth. So you have like zigzag behavior. Whereas if you use momentum, you can really do a much better job in terms of finding, going through the ravine. And hitting the local optimum much faster. Momentum is one of the most commonly used because it's so simple to implement. And it's, when we use convolutional networks, it's stochastic gradient descent with mini batches with momentum is super hard to beat in practice, right? Yes, question? 0.9.
That with the size of the mini batches though, because aren't mini batches smooth?
Remember the size of the mini batch, if you're using 128, excuse me, if you're using 128, if you're using 256, you still average, right? So you compute the gradients for 128 or 256, and then you divide by 128 or 256. So your gradient is always, the units of the gradient is always per example, right? But when I say 0.9, I really mean 0.9. I mean, sometimes people use 0.8, 0.7, you know, so it's sort of, it's a hyperparameter that you have to play with on the validation set. And then again, it can get past plateaus more quickly by gaining the momentum, right? Because it looks at the previous gradients estimates, and current gradient estimate, and so forth. Adaptive learning rates. There's been a few papers recently, just in the last 3 to 4 years, of how can you actually build adaptive learning rates, right? Because maybe a learning rate of 0.1 is not just always using it is not a good idea. So in particular, you want to have learning rates that one learning rate per parameter. So if you have 1 million weights in your model, you will effectively want to have 1 million different learning rates. One particular paper that was published, I think, a few years ago called Adagrad. And it says that the learning rates can be scaled by the square root of your cumulative sum of squared gradients. Okay, so let's look at it. This is your gradient, right? You take your gradient, you look at the square of the gradient, and that looks at the cumulative square of the gradients, okay? And then your gradient itself is taking the gradient divided by square root of this term here. I think there is a normalization here divided by t that's missing here. But what's the intuition? And there are a bunch of different ones that I'll show you, but what's the intuition here? Any guesses? Think of it as follows. On average, this term here is like the variance of the gradients, right? Because on average, the gradient is going to be pointing at the 0. So the sum of the squares, it's like a variance. So what this is saying, this is essentially saying, if my variance is small, right, then what I'd like to do, I'd like to increase my learning rate, because one of a small variance is going to be high value. So that basically says that if my gradients don't change as much, I want to have high learning rate. If my variance of the gradients is high, you know, 1 point, 1 time step, but like big gradient this way, another point is big gradient that way. In this case, this variance term is going to be quite large, which basically means that the gradient is going to be scaled down by the variance, right? So whenever variance is high, you want to use small learning rate. Whenever your variance is small, you want to use large learning rate. And then there was another algorithm called RMS-prop that instead of cumulative sums, you use exponential average, right? So you're sort of doing this term here. So you're taking the weighted average of the previous times the sum of the squares, and then you're doing this update here. There is a hyperparameter epsilon, which is basically, it's also an important hyperparameter. I think if you set it to 0.1, it usually works pretty well. Somehow 0.1 and 0.01 are pretty good numbers to remember whenever you're training these models. But in general, again, it's the same idea, right? And then there is ADAM, which is the most commonly used optimization technique. Like if you look at TensorFlow and so forth, there's like a flag, use ADAM, which is basically combines exponential RMS-prop, which looks at the exponential average, with momentum. Okay, so this is the most commonly used technique for optimizing these models, which is basically exactly the same as this update plus the momentum. But again, what I'd like you to remember is just this notion that you're looking at the variance of the gradients. And if the variance is high, you want to use small learning rate. If the variance is large, you want to use small learning rate, which makes sense, right? Because most of the time as a researcher, you would look at the optimizer, and you see your gradients do this. You say, whoa, the gradients is too high, shrink it. Or when you're looking and you see, you know, your gradients kind of like a very small, right? The objective function is not changing as much. You say, well, increase the learning rate. This just does it adaptively for you. Okay? Gradient checking. This is another very important thing to keep in mind. Sometimes, whenever you write your own code of backprop, what you can do is you can use a finite difference approximation to the gradient. In fact, for your own homework, if you want to check your gradients, there are functions called checkgrad. Like if you Google checkgrad, there is one in MATLAB, there is one in Python, which essentially implements the finite differences method, right? So what is it doing? It's basically saying if you have a loss function and you have a parameter, right? You take some small epsilon, you add to x, you take some again small epsilon, you subtract it from x, and then you're saying the gradient is approximately going to be given by this expression, right? Sometimes people call it, it's a finite differences. So that's really checking whether you've computed gradients correctly. That's a very useful tool. Of course, today, if you're using like PyTorch or Caffe or TensorFlow, a whole bunch of different tools, they already do it for you. So you don't have to compute gradients on your own. But in many cases, this is a very good technique to just double check that your gradients are correct. Because in many cases, your gradients might not be correct. But if you look at your loss function can still go down, right? So just because of randomness and maybe pointing in the right direction, so it's really useful to do this debugging. Yes.
Are there situations where that would suffice for finding a gradient?
No, because it's very expensive. But the other thing that I've learned is that if this checks out, this still doesn't mean that your gradient is correct. If this doesn't check out, then you know something is wrong with your implementation for sure. Yes?
So if your gradient is incorrect, is it possible that you do, like your training loss is decreasing and your validation loss is also decreasing?
Yep, it's possible. So gradients might not be correct, or maybe parts of your gradients for certain parameters might be correct, and so you kind of still could see the training decreasing and the validation decreasing, probably not to the optimum one, but that could happen, yeah. Yes, maybe last question and then we'll move on. Yeah?
Are there any of these optimization techniques that are best for noisy data?
Noisy data. Not as far as I know. I mean, whenever you have noisy data, you have to deal with the noise somehow. I think that during the second half of this course, we're going to look at generative models precisely designed for dealing with noisy data. These sets of techniques are not very robust to the noisy data. We'll see some examples of how we can deal with it, but it doesn't have to do with optimization. It has to do with the model definition, what models you're building of noisy data. Okay, the other thing that I want to point out is that it's also useful to debug on a small data set. Let's say you make sure that you take a small data set and make sure you can overfit on your data set. So if you take 500 or 1,000 examples and you're using your implemented backprop, make sure that you can hit zero training error, right? That's a very good tool for debugging optimization, right? Because if your model complexity is large enough and you have small data set, your training error should be zero. If you're optimizing it and you don't hit zero training errors, something is wrong with your optimizer, right? And that's a very good, a lot of people are using this for debugging, just to see, can you overfit on a small training set? If not, you have to investigate the following. Now, some of the units get saturated even before the first update, because sometimes some of the hidden units, if you don't initialize your parameters properly and using sigmoids or 10H or even ReLOs, some of them can have very big numbers. Then you have to scale down your parameters, you have to normalize your inputs. Is the training error bouncing up and down? You do the update, your training error drops, next update, your training error goes up, and it's just this zigzagging behavior. In this case, you have to play with your learning rate. And then this doesn't mean you've computed your gradient correctly, you could still overfit with some of the gradients being wrong, right? So that's where finite differences come in, some checking mechanisms that you've computed the gradients appropriately. Okay, now, in today's lecture, I need to cover these techniques, dropout and batch norm, because that's part of your homework that you're going to be implementing. Yes?
What is the exact meaning of the sum of the units saturated in the previous one?
So some of the units get saturated. Basically what that means is that imagine you have a sigmoid function, sigmoid activation function, right? And imagine that I initialize my weights to be 1,000, okay? So no matter what the input is, like let's say my input is 1 or -1, I multiply it by 1,000, and then I'm just going to be saying the probability of this unit is always going to be 1, regardless of the input. Even if I give you 0.01, it's going to be 1. If I give you 10, it's going to be 1. If I give you 0.05, it's going to be 1. So that means that sometimes units can get saturated because your weights are large. And this is very bad because that basically means that you somehow pushing your model into regime where it's very hard to do optimization. It's just units get saturated. You don't want that behavior. Okay, so let's look at some more advanced and recent techniques which really make these models work much better. So there is really, if you think about the optimizer for these models, it really is stochastic gradient descent with momentum, with adaptive learning rates, plus dropout and batch normalization. Okay? Once you combine all of these techniques, you basically have state-of-the-art optimizer. It's very hard to do anything better than this. Okay, now before I get to that, let me just give you a little bit of intuition of what these models are doing. So deep learning is a research in learning models with multi-layer representations, right? So these are multi-layer feed-forward neural networks. These also correspond to multi-layer graphical models, such as belief networks, Boltzmann machines, something that we'll cover in this class. Each layer learns so-called distributed representations. So what does that mean? That means that units in each layer are not mutually exclusive, right? So for example, if you think about k-means, clustering-based approaches, then a particular point can just belong to one cluster, right? In these representations, each unit are not, like all of these units are not mutually exclusive. Each unit is a separate feature of the input, and then all of them can be activated. And two units can be active at the same time, unlike clustering-based methods, for example. Units do not correspond to partitioning of the input or clustering of the input, right? And again, in clustering, an input can only belong to a single cluster. So it's not like you're trying to partition your data somehow. You're just trying to find features that can co-activate. So here's an example. If you look at clustering, nearest neighbor methods, support vector machines, local density estimators, what essentially a lot of these methods are doing is that you have some high-dimensional space, you're partitioning the space, and then you have these learned prototypes, right, for each particular region in the space. And these models have their advantages, but the number of parameters for each region typically grows with the number of regions is linear with the number of parameters, right? So the more regions I have, the more parameters I need, roughly speaking, right? And distributed representations, both machines, factor models, principal component analysis, sparse coding, deep models, all of these models are learning these distributed representations. Think of it this way. If I have an input, this input can partition, this particular hidden unit can partition, the space into two classes, right? C1 and C2. If I have a second hidden unit, the second hidden unit can do the partitioning. So now you have 4, points or 4 partitions. If I get the third unit, I'm partitioning it like this, then you can have, these regions, right? So you can roughly see that as you add the number of hidden units, you can have this almost an exponential partitioning of the space. So each parameter affects many regions, not just local. So each unit, each feature is not just a local feature like the ones here. And the number of regions grow roughly, now it's roughly exponentially with the number of parameters, right? So if I have, in principle, if I have 10 hidden units, there are 2 to the 10 possible configurations, right? If my units are binary thresholds, 2 to the 10 possible partitions. So it has advantages, it has disadvantages, right? Depending on the problem that you're trying to solve. And this is also a little inspiration from the visual cortex, where in the visual cortex, you basically have, for those of you interested in neuroscience, there are actually multiple levels of processing. So it seems like in the visual area, in the first visual area, in the human brain, you're basically doing some form of simple edge detection, corner detection, right? There are some neurons that are really firing, like when you see the edge or some corners. It's very important. And no, this is sort of like the idea that you have these edges, and then you have some high-level representations, like you start understanding something about eyes and noses and so forth, and then you start recognizing the face. So there is V1, V2, V4, and so forth. of course, nobody knows how the human brain works. It's just an inspiration. And just to show you some of the success stories very quickly before we dive into the definition of the dropout, this was done by the Microsoft Speech Group. And it's kind of interesting. In the 90s, you had speech recognition systems, and as you were using, they were improving steadily over time. And then since 2000, basically the whole thing was flat. There's no improvement. So that's why speech recognition never worked. It kind of worked and kind of doesn't, right? Like it never was working good enough for you to use on your phone or. And over the last 5 years, there's been kind of deep increase in accuracy, or in this case, the error rate we're decreasing using word error rate on a specific benchmark. So you kind of like have quite rapid improvement in speech recognition. Here is another example that we'll cover in the next couple of classes when we look at the convolutional networks. This was done, this is an ImageNet network, and in 2012, a group from University of Toronto headed by Jeff Hinton, they've developed this model that basically worked remarkably well on recognizing images. And that completely switched the whole computer vision field from being very anti-deep neural networks to the conference, basically everybody's using deep neural networks because there's nothing else that works better than these models, at least currently. But if you look at some of the examples here, like this is an example of a mite, and the model correctly predicts it as a mite. Or this example of container ship predicts container ship. Or leopard correctly predicts leopard. These are some examples where the model fails. Like if you look at this example, it predicts it's cherry, but the right answer is Dalmatian. Right? So you can sort of see there is also a lot of noise in these examples. Or this is an example of Madagascar cat, and the model predicts it's a squirrel monkey. Right? So, which is pretty good. I mean, how many of you know the difference between Madagascar cat and squirrel monkey? But I think that if you actually train yourself, you could probably do better than this model. So let me hypothesize why training is hard. So one of the hypotheses is that it's a very hard optimization problem. Right? The reason why is because when you have many, many layers, backpropagating gradients, this problem of vanishing gradients becomes a big problem, right? So vanishing gradient problem, saturated units block the gradient propagation, and this is a very well-known problem, particularly in recurrent neural networks. Now, generally it is true, so if you look at more recent architecture like residual networks that introduce skip connections between the layers to help propagation of gradients through the network, that's, speaks up to that hypothesis, right? The training is hard. So we kind of like suffering from underfitting model. The second hypothesis is overfitting. It's kind of like complete opposite of the first one. And what it does is we're basically saying that we are exploring a space of complex functions, right? And I don't mean like complex, I mean like very difficult space of functions. Deep nets usually have lots of parameters. Right? So when we train models, we look at some of the state-of-the-art models, these models have millions of parameters. And so we might be living in this regime where we're training these gigantic systems and overfitting is a problem. And for the first hypothesis, there's a little bit of research, a lot of research actually, on using better optimization tools. Right? So for example, batch normalization is one tool that allows us to improve optimization quite substantially. There is a number of second-order methods, such as KFAC. These are a little bit more advanced techniques that are trying to approximate Fisher information matrix so that you can get to the second-order optimization methods. You use GPUs, you use distributed computing, so you're really trying to train these models much more efficiently. The second hypothesis is overfitting and to use better regularization. So for example, you can use dropouts, you can use unsupervised pre-training, and then from many large-scale problems, you'll need to use both, better optimization and better regularization. So what's happening in practice is that if I give you a data set, and I tell you, build me the best model on this data set, what would you do? Well, the rule of thumb, at least in practice, is that first you try to build the most complex model so that you actually get zero training error on this data set. In fact, most of the models on ImageNet that have, the dataset has about 1.2 million images. Most of the models that people are introducing can have zero training error. They can perfectly overfit the training on the training, right? So the first thing you do is you build a model which is complex enough to overfit on the training set. And for that, you need to have good optimization techniques, right? You need to be able to optimize these very large scale models efficiently. And then what you do is you start adding regularization. And so you start controlling your model complexity to the point where these models generalize much better, right? So that's kind of what's been happening, at least in practice. You start with a very large model, and then you try to regularize it. So you need to do good regularization, and you also need to have good optimization methods so that you can fit these large-scale models more efficiently. Traditionally, from statistics viewpoint, you start with model complexity, you try to fit the simplest possible model, and then you try to expand. For these models, kind of the other way around. You start with the most complex one, and then you try to regularize it. Yeah, there was a question?
How does unsupervised training prevent model from the
Yeah, I'll come to that. So let's look at some of these examples. So let's look at first at unsupervised pre-training. Okay? So what you'd like to do is you'd like to initialize hidden layers using unsupervised learning, right? So let's look at the following. You're forcing the network to represent latent structure of the input distribution. So you can ask the following question: why this is an image of 2 as a character and this is not? Right? Obviously, there is no structure here. So what you'd like to do is you'd like to encourage hidden layers to encode this structure. Right? And that can prevent overfitting because you're forcing your network to say, whatever structure I'm seeing here, my hidden units should respect this structure. So let me show you how you can do that. And this is a much harder task than supervised learning, than just classifying what this is. So you'd expect less overfitting. So let me show you what people are doing. So the feed-forward neural network here is trying to reproduce its input as the output. Right? So this is known as an autoencoder. And we'll come back to autoencoders later in this class. But the idea is the following. You have your input. It's a one-layer neural network. You take the weighted average. You pass it through the sigmoid function. And then there is a decoder. You take this output of the encoder. You take these weights, multiply it by W transpose, pass it through the output, whatever that might be. I'll say logistic if you're working with binary data. And you look at the reconstruction. Right? So this is just a sigmoid for binary units. And so the loss function for binary hidden units would be cross entropy, right? And so what you're trying to do here is you basically, if you're working with real valued numbers, you're trying to do reconstruction. You try to achieve as good reconstruction as possible, right? Think of it as follows. I give you the data, and you pre-train your weights to map to the hidden units such a way that you can reconstruct the data, okay? In the case when you're working with real valued data, this is just sum of square differences. If I go back here, obviously I have to put some constraint on these hidden variables in general, right? Because if the dimension of x is the same as dimension of h, then I can just copy, right? I can just use the identity, copy it here, use the identity, and I have perfect reconstruction. So there's a lot of work people trying to figure out how we can constrain the space, sparse coding, we enforce sparsity, and so forth. And then you can use this layer pre-training. You can say, well, train one layer at a time with this unsupervised idea, fix the parameters of the previous hidden layer. So the way you do is the following. You're training this layer to reconstruct itself, right? It's called unsupervised because you don't need labels. You're basically saying, find me the hidden variables in such a way that if I reconstruct, I can reconstruct back the original digit or the original input. And then you go in and say, you know what, now I'm going to do the same objectives here. Apply the same objective here. Reconstruct these hidden states as good as I can, right? So go up and down to the reconstruction here and so forth. So that gives you pre-training of a model, and you're forcing a particular inductive bias, right? You're forcing an inductive bias that says, make sure that you can explain the data as good as possible. Make sure at least you can reconstruct the original input. Yes?
For each layer, are you training it to reproduce the original input, or?
No, just a layer. Just a layer, yeah.
The previous layer?
Just the previous layer, just the states of these ones. So it's fairly efficient. There are a whole bunch of variations where people build deep autoencoders to try to go all the way down to the input and so forth. But for most of the cases, you can just do simple layer-wise pre-training. Now, this model has some caveat, and this sort of makes a connection to generative models, right? Generative models in the sense that you're trying to predict all the pixels in your data, right? Which is a much harder task than classifying the digit, because you have to perfectly predict all the pixel locations. If this is a mean over 2, you have to predict all the locations where these pixels should be active, right? And so one caveat here is, for the unsupervised pre-training, your first layer finds units that are more common in training inputs than the random inputs. So you try to reproduce your inputs. The second layer finds combination of hidden units features that are more common than random hidden units features and so forth, right? So that initializes the parameters in the region such that then, it can overfit less to the data. Particularly, this technique works well if you don't have a lot of labeled examples, right? This technique doesn't work well if you actually have millions of labeled examples. So generally, in the cases where you don't have a lot of labeled examples, this can work quite well, right? Because you're forcing your hidden states to explain something about the data. If you believe that's a good inductive bias, then you should use that. And then what you can do is you can add the output layer, and then you just basically train the entire model, right? You just use the forward-backward algorithm. You just do backpropagation, and the last phase is called phi tuning, right? So you're tuning the supervised task for a particular task that they're trying to solve, like a classification task. Okay. Now let me get to the dropouts. Like, this technique is much more important for training these deep networks. So the key idea behind dropout is you want to cripple your network by removing hidden units stochastically. Okay? So each hidden unit is set to 0 with probability 0.5. You flip a coin and you shut down a hidden unit. So what that means is that these hidden units cannot co-adapt to other units. And that turns out that the network is learning features that are more useful, right? Because you can't have two units that are co-adapting. You can't have two units that basically say, well, if this present, then this should present, and now I can classify it as a digit. Because I can randomly remove one of them, and the model should still be able to classify correctly with just one feature, right? So it generally builds more robust features here. Yes, maybe quick question.
First, is this harder to train?
So let me get to the training of how this is training. Now the question also is, why do you have to use probability 0.5? Any guesses? What would you use if you were using this technique?
Something less.
Like 0.2? So I think that 0.5 usually works quite well. And it's a really good number when you're publishing a paper. Because if you had to choose a number between 0 and 1, what would it be? 0.5. So reviewers don't ask any questions. If we said use the dropout rate of 0.3675, right, then there would be questions like why 0.3675? Whereas 0.5, no questions. And it actually works pretty well. Like, sometimes people use 0.2, 0.3, depending on your model and your architecture. That's another hyperparameter to use. But 0.5 works pretty well. So let me let me actually show you how you implement this particular model. So let's say you have layer pre-activation. Sorry about that. You have layer pre-activation. And then when you're activating your hidden units, you're just multiplying it by a mask, which is a random binary mask. So for every time you initialize your random binary mask to be just randomly 0, 1 with probability 0.5, and then you just do element-wise multiplication. And then the output is this function. So it really changes one line in your code to implement dropout, right? If you're using with a batch, you have 100 examples in your batch, and you have 1,000, let's say, parameters, or 1,000 hidden units, then you would create a mask of size 100 by 1,000, right? And then whenever you're doing this calculation, you're just updating your hidden states and you're randomly shutting them down. Backpropagation algorithm. The reason why people use dropout is because it's actually very simple to use in a backpropagation algorithm, right? Remember what the backpropagation algorithm does. You have your loss function, you compute the gradients, with the hidden layer, you compute the gradients with respect to the parameters and the hidden layers and so forth, right? And you compute the gradients with respect to the layer below. So remember, all of this stuff is the backpropagation algorithm that you're implementing, right? And so now, what happens here, this particular hidden state will already be 0, which includes the mask, right? So whenever you do forward pass, 50% of your hidden units will be 0. So you don't really have to do anything in a backward pass, because when you do the backward pass, some of these states are going to be 0. And that's all. So really, to do the dropout, you just need to implement the feed-forward mask. Set it to 0. Remember the states of the hidden units. Most of them are going to be, half of them are going to be 0. And then when you backprop, you don't really need to change anything. So it really requires you to change one line in your code to implement dropout. Dropout at test time. What do you do at test time? Well, your test time is you're going to be replacing these masks by their expectations. So this seems to be the constant vector of 0.5 if the dropout probability is 0.5, right? So what that means is that if you're using a dropout probability of 0.5, then essentially, on average, if you have 100 units, then 50 of them are going to be active, 50 of them are going to be inactive, right? So what that means at test time you're going to be using all of them, but you're going to be dividing outgoing weights by 2, right? So on average, on expectation, it still is the right input, right? So you're not going to be using stochastically sampling it at test time. At test time, you're going to be using the entire network. You're just going to be scaling up outgoing weights by 2, right? And for a single layer, it's equivalent to taking geometric average over all neural networks with all possible binary masks. If you think about it, let's say you have 100 hidden units, right? There are 2 to the 100 possible configurations if you're using dropouts, right? In principle. Whenever you are, if you could take a geometric average over those 2 to the 100 different networks, that's effectively what the dropout is doing in the propagation of the mean. It's not quite the right because of the nonlinearities, but on average, it's like taking the exponential average of all of these networks. Yeah, is a question?
So you said that if you do dropout and separate out the different neurons as the ones which no activation and the ones with activation, and they'll be randomly generated, could you use 2 different mini batches on them?
No, the point is that for every single example, you have to generate a new random mask, right? Every time you see an example, it's a random mask. So even if you see the same example twice, you're going to be using 2 different random masks. That's important, right? So at every time you see an example, you randomly kill 50% of the hidden states. And again, there's some variance. It could be more, it could be less, right? And so it beats regular backpropagation on many data sets and can be viewed as a geometric average of exponential number of networks, right? Because you have exponential number. Think of it as exponential number of different networks, because every time you kill some units, there are 2 to the number of hidden units possible networks, and then you just take the average over those. And essentially, that's what dropout is attempting to do. Yes?
Doesn't this imply that it's really hard to train?
The what?
Doesn't this imply that it's really hard to train?
It's harder to train than backpropagation, but it's not that hard. Because your code doesn't really change, it takes longer. But it does find much better features, and it does find much better representation. And on your second homework, I think you'll play with backprop, with dropouts. So you'll implement dropout, and you'll see how well it performs. Let me just maybe I can just get to the rest, and maybe I can answer the question at the very end if that's okay. Otherwise, I won't go through the batching on what that you need for your homework as well. Okay, batch normalization. Let me go through another trick. This is another very important technique that was developed a couple of years ago, and it's the following. Normalizing inputs will speed up training, and that people have known about this, right? If you normalize your inputs, otherwise optimization becomes much harder. The question is, can normalization be useful at the level of the hidden layers? So can you somehow normalize your hidden layers? And it turns out that the batch normalization is an attempt to do that. It was published by those guys in 2014. And it's a very simple idea. Each unit's pre-activation is normalized. You subtract the mean, divide by standard deviation. During training, mean and standard deviation is computed for each mini batch. And backpropagation takes into account this normalization. And at test time, you use global mean and standard deviation. Okay? So let's look at precisely the definition of batch normalization. So what is the batch normalization really doing? Let's say you have values of x. And by the way, I would encourage you to read this paper. I believe for your homework, you actually have to do batch normalization. Is that right?
Yeah.
You do? OK. Read this paper. That can clear up a lot of things as well. But what is the batch normalization really doing? Let's say you have values x over the mini batch. And these x could be the states of the hidden units. It doesn't mean it's an input. It could be states of the hidden units. And the parameters, you also have these two additional parameters, gamma and beta, per hidden unit that you're trying to learn. So for a mini batch, you take the average of your hidden units, right? So let's say you have a mini batch of 128. You pass it through the network. You compute the mean for each hidden unit. You compute the variance for each hidden unit, right? According to your mini batch. Let's say you have 128 in your mini batch. And then you use this operation. It's the state of the hidden unit minus the mean divided by the variance plus some epsilon. This is a hyperparameter again. And then the output of the hidden unit is going to be gamma times x plus beta. Typically, you'd initialize beta to be 0 and gamma to be 1. Okay? So think of this as an additional layer in your network. You have some hidden units, and then you have a normalization layer. And this normalization layer just performs this operation. This normalization layer really subtracts the mean, divided by standard deviation, multiplies by gamma, adds beta, and now this is your representation of the hidden units. And then again, you take the weighted average, pass it through nonlinearity, you get to the next layer. Right? So it's almost like injecting an additional normalization layer. Now, this particular linear transformation can adapt to nonlinear activation functions. So gamma and beta are trained here. Right? In principle, if the model didn't want to use this normalization, it could set beta. It could learn beta to be mean, and it could learn a sigma to be variance. In which case, it could undo the normalization. It doesn't happen very frequently, but in principle, the capacity of the network is not somehow diminished. But if you have 1,000 hidden units, you're going to have 2,000 additional parameters, right, that you're learning. But in the grand theme of scheme, it's not that many number of parameters, right? Think of, you have 1,000 hidden units and by another 1,000 hidden units, so you're learning 1,000 times 1,000 matrix, right? So matrix of 1,000 times 1,000, what is it, 1,000,000? Yeah, sounds about right. So compared to 1,000,000 parameters that you're learning, additional 2,000 parameters don't really make much of a difference, right? So that's an additional layer, and you could backprop through this layer. So you have to backpropagate through this objective function. You have to backpropagate through x hat, so you have to compute the gradients of this guy and this guy, right? If you look at the paper that's cited here, the equations are there, so you can just implement them yourself. Okay, so batch normalization. Why normalizing the pre-activations? Well, you want to keep pre-activations in a non-saturating regime, right? So what the batch normalization is doing is it's basically saying that I want to normalize each layer such that the activations are 0 mean, standard deviation 1. So you never run into this problem of saturation, or because the units are always tend to be in the right regime. And that's precisely why these models work so well in terms of optimization, because your network is always sitting in non-saturating regime, and it can really help optimization. Why mini batches? Well, hidden units depend on parameters, and you can optimize mean and standard deviation for all, and it also adds stochasticity to the training. So, in practice, people do use mini batches, and so you have to compute mean and variance per mini batch. You can't really use one example because there's no mean and variance, So people tend to use 128, 256 number of examples to do this normalization. How do you take this normalization at the backprop? You basically have to find derivative with respect to these hidden units. And it depends on the partial derivatives of both the mean and the standard deviation. You have to update these hyperparameters. Okay? So that in itself is just a little bit of algebra that you have to do. Hopefully you guys are all familiar with calculus and you can backpropagate derivatives through these equations. You have to remember that you take derivatives of 1 over x, it's like, 1 over x squared minus stuff like that, right? You can look up in the books of how to do derivatives. Now, how to use, why do you want to use global mean and standard deviation in test time? So when it comes down to testing your system, right, what you want to do is, if you go back and you see what are the mean and standard deviation, what typically you do is you run your entire training set through the network and compute mean and standard deviation per hidden unit in your entire network, and then apply these ones to your test set, right? Does that make sense? So it also removes stochasticity of mean and standard deviation. It also requires the final phase where from the first to the last layer, you basically have to propagate all the training examples and then compute and store all global means and standard deviations, right? And then generally there's been some papers that showing, instead of using this global mean, you can also use running average. Or instead of using just mini batches, mean and standard deviation, you can also use momentum, or you can also use sort of running average, exponential moving average of those. So there are some tricks to improve batch norm. But you'll get to play with a basic batch norm, and you'll see that it should perform much better. At least optimization should be much more stable. Okay, in the last few minutes, what I'd like to do is I'd like to show you some of the optimization tricks, and then maybe we can have a few questions. Stochastic gradient descent with momentum, batch normalization, dropout, and using adaptive learning rates like ADAM works really well, right? It's extremely hard to beat that. In fact, a number of papers that have been published that are trying to use second-order methods and more, advanced techniques, the first thing reviewers are looking for is, have you implemented this? And if you did, what are the numbers? So that works remarkably well. Learning rates, you want to pick your learning rate by running on a subset of the data, just like as we've seen before. You can start with a large learning rate, divide by 2. You want to decay your learning rate by a factor of approximately 100 by the end of training. So there's some things that you have to take into account. In many cases, people tend to use ReLU nonlinearities. For your homework, I think you're going to try both sigmoids and ReLUs, right? And that's why I'm saying that you should start working on your assignment today, because it's not like, you actually have to run a whole bunch of experiments. And if you've never done this, it will be frustrating. It's not like, you try to solve a convex optimization problem, you know what the answer is, there's a tool, no matter where you start, you get the right answer all the time. This is, depending where you start, how you optimize, you can end up in very different local optimum, right? So it takes a little bit of time to actually run these systems and then see what's happening. Improving generalization. Weight sharing, later on we'll talk about convolutional neural networks. Dropout, weight decay, if you want to use L2, regularize it, you should. Sparsity in the hidden units, we haven't talked about sparsity in the hidden units, but there are some penalty functions that you can incorporate as well to sparsify the states of the hidden units. One of the things that you should do as you're training these models is you want to visualize. You want to check gradients numerically, as I said before, but you also want to visualize your features. So features have to be uncorrelated and have to have high variance. So let me show you an example. This is what an example of a good training would look like. So here you have samples, and here you have hidden units. Okay? And this is the sigmoid activation function. Black means it's close to 0, white means it's close to 1. So for example, look at cross samples. Like for this sample, this unit gets activated, and this unit gets activated. Second sample, these units get activated, and so forth. And so you see that they are not very correlated from example to example, right? You also don't see saturated units. You don't see a hidden unit that's white, for all the samples, or black for all the samples. Yes?
But wouldn't you see that if you had a bunch of samples of the same class in the top of the matrix?
No, not really, because so this is an example of MNIST data set, and there are some examples of 2s and 3s. There's only 10 digits, but they still pick up on different features. Let me just show you an example. Let me actually skip. Here's an example before I get to the previous one. Here's an example of a bad training. Okay, so what are you seeing here? You're basically seeing here that across samples, there is a high correlation between the units, right? So this sample pattern activation and this sample pattern activation is pretty much the same. That's really bad. Sometimes you also see this unit is black all the time, right? So it basically takes 0 no matter what the input is. It's useless, right? You can basically see it's a useless hidden unit. Because if for all the training example, this particular unit is 0 all the time or is 1 all the time, it doesn't really communicate any information, right? So sometimes when the units get saturated between 0 and 1, they're meaningless. They don't really tell you anything. And then you can, you can also see that some hidden units, it's just either saturated or they have this pattern which is really bad. This is a bad training unit. Many hidden units ignore the input, exhibit strong correlations. You want to avoid that. A couple of things. You want to visualize parameters. Should it have been structured and should be uncorrelated? So for example, what I'm showing you here, let's say you're doing MNIST data set, right? These are 28 by 28 images. There are 784. The input size is 784. So when I look at a particular weight that's connecting 784 numbers to a particular hidden unit, right? That's a vector of size 784. If you reshape it into 28 by 28, it should look something like this, approximately. For MNIST, it will look a little different, but you should start seeing, that the model is picking up some edges, or it's not just random. It's not like this, right? So it's useful to visualize, at least at the first layer, is the model capturing some structure in the data? And you can visualize, primarily when you're working with images. Or if you see something like this is really bad, right? Because it's just not really capturing any structure. Or it's noisy, there's no structure, it's just a bunch of random things that the model is discovering, right? Okay, does it make sense? Yes, question?
Does this contradict with the idea of dropout? Because we need different units to capture different structures, like in the images. But when we use dropout, we turn off some of the structures. So we need other units to capture these specific kind of structures. Is there a contradiction?
I don't think there is a contradiction, because what happens, and you should do it with dropout. Once you do it with dropouts, you should visualize what these units would look like. What you will see is there is a little bit of redundancy, but there is a lot of uncorrelatedness. These units tend to be a little bit more orthogonal, because if you kill some of them, the model can still classify the digit correctly, right? So you're discovering features that are independent, that are to some extent orthogonal. And I think that's very good to prevent overfitting or to prevent co-adaptation of features. So as an example, again, for your homework, you will see some of that. And again, you visualize your parameters. You should measure the error both the training and the validation set. So you should look at the performance on the validation set as well. And you want to test on small subsets of the data and check that the error is going to 0. When it doesn't work, training diverges, let's say, learning rate may be too large, so decrease the learning rate. Or your backpropagation is buggy. Check your gradients. Parameter collapse, loss, and so forth, check your loss function. Is it appropriate for your objective that you're trying to optimize? For your homework, you're going to be using cross-entropy. But for other data sets, is this the right loss function? Does it have degenerate solution? If your network is underperforming, compute flops in number of parameters. If too small, make it the net larger, right? In many cases, maybe you're just underfitting. You want to visualize hidden units parameters, so it's the fixed optimization. So there's a lot of different things you can do. And if your network is too slow to train, then you want to be using GPUs and distributed clustering, distributed frameworks, or make your networks a little bit smaller. You don't have the luxury of doing that for this class, but nonetheless, the networks that you're going to be building up should be good enough to train on the CPU. Okay, in the last 10 minutes, what I'd like to do is, any questions, by the way? Because this is something that you're going to be doing for your homework, the first step. So there's a lot of things that you should be digesting. Yes, question? By global, I basically mean that you have to run entire training set through the network and then compute the mean and standard deviation for every single hidden unit. So that's why it's called global, because you're actually looking at the entire training set, not just some mini batch. So you remove stochasticity completely from testing. Because whenever you run your network in real time at test time, you don't want to have any stochasticity in there, right? Unless there is specific, you're trying to estimate uncertainties and so forth. Yeah.
Yeah, I want to ask something about the dropout. I see in the most studies, people use only one dropout rate upon the whole network. So is there anybody try to use different rate at different levels?
I think that generally you can use different rates at different layers. The question is, how do you find what these rates should be, dropout rates, right? So maybe you have a mechanism to try to do it adaptively or build another learning algorithm that tries to adapt it. But the reason why people use a standard dropout rate, just because it's easier. It's only one hyperparameter to fit. If you think about, you have to think about learning rates. You have to think about, layers, the architecture. You have to think about, tricks and optimization. What's your momentum? You have to think about your dropout rate, right? You have to think about these epsilons when you're doing batch normalization. So there's a whole bunch of different hyperparameters that you should really think about. And these hyperparameters are different for different problems. Depending on the problem that you're trying to solve, they could be different. So that's why people if you start adding per layer dropouts, that just increases the number of hyperparameters you have to search. Yeah, there's lots of work. People are trying to use design methods for automatically tuning hyperparameters. There's something called Bayesian optimization that's been somewhat successful. In practice, what people tend to do with a lot of resources is to just do grid search. You fire up 1,000 jobs with cross, with different hyperparameters, and then you just basically get the best one in parallel. So, yes?
If we implement our homework correctly, is it the training speed and accuracy, is it gonna close to using TensorFlow or?
Yeah, it should be close to, if you implement it correctly, you should actually have your learning rates on your training set should be quite small. That's one hint I can give you, right? It shouldn't be 20% error or something like that. It actually should be pretty reasonable. You will see it's not a very hard data set for you to try on. You can also try TensorFlow and PyTorch to just benchmark the numbers and so forth. So that's okay. But you cannot submit your assignment using TensorFlow, right? You actually have to implement your own optimizers. Yes?
When you visualize the parameters for the second hidden layer, basically the first one is quite obvious. It will pick up the edges, etc. But for the second one, it will be less meaningful for the
Yes.
So how do you define its randomness or its?
Yeah, so it's a good question. How do we visualize the second layer parameters? There isn't really a good way to visualize. In many cases, you would probably just visualize this pattern, just to see, are there some hidden units that are saturated and so forth.
Also, actually, for this figure, basically, if your sample have the same classification, so does it mean it should be if it's in the same category, it should have the same active?
Not really. In many cases, maybe some of the activations are going to be similar, but you should also see different activations. Because if you look at, for example, 3, It's not just a template tree. People write trees in different ways. It's like curved tree, rotated tree, small tree. It has a curve at the end and so forth. So you will start picking up on a lot of different features. You will probably see some correlation between all the threes and all the twos, but at the same time, it shouldn't be like this.
But I mean, if it's very near to the output layer.
Yeah, if it's very near to the output layer, you'll start seeing more and more correlations, for sure. But it still should be sufficiently, not exactly like, replications. Yes, maybe last question.
Still about the global mean and variance of the measurement. So, what if the overall testing dataset not into the memory?
No, you don't need to, whenever you compute global mean and variance, you don't need to compute it for test set. You just need to store the mean and standard deviation. So if you have 1,000 hidden units, you're going to be storing 2,000 additional numbers.
You mean store all of these numbers very quickly and then just use the average of them?
That's right. Yes.
Are the samples along y-axis close to each other? Like, are they similar? If two samples are similar, should we expect the same hidden unit activation?
I mean, if two samples are very similar to each other, then yes, you would. But if you take a random subset from your training examples, then they shouldn't be, you shouldn't see a lot of correlation. You'll probably see some correlation, but you shouldn't see a lot. Right? If it's a random sample from your training set, you will still, for example, for something like MNIST, you'll see something like this or something similar to this. Okay, so let me kind of in the last, maybe just in the last 5 minutes, quickly show you a few paradigms. So supervised learning. This is a setting where, and then we can probably continue in the next class. Supervised setting is where you have, at training time, you have data, and data is of the form X and Y. Right? You have some inputs, you have some target outputs. And this is the setting where X and Y come from some distribution, some joint distribution of X and Y. Okay? And at test time, you have exactly the same setting. Right? The data comes from X, from this distribution, and you're trying to, you don't have Y, but you're trying to predict Y given X. Right? So for example, classification, regression, that's the setting that you're operating on. Unsupervised learning. In unsupervised learning, you have some data, X, you don't have targets Y. And X comes from some underlying distribution. At test time, again, you have some data, X, which comes from the same distribution. Right? And for example, distribution estimation, dimensionality reduction, maybe clustering, and so forth. Right? The important point is that they both come from the same distribution. Semi-supervised learning is an interesting one. This is a setting where you have some labeled examples and unlabeled examples. And then these labeled examples, they come from the joint distribution, and unlabeled examples come from the marginal, P of X. Right? So this is not different compared to this. These come from the same distribution. At test time, again, some examples might contain label, some examples might not, and it's exactly the same setting. So notice that whatever you have at the training, you have exact same thing at the test. Oh. Multitask learning. This is an example where you have an input and you have multiple outputs. So instead of just doing like classifying digits as to 1, 2, 3, 4, 5, maybe you also want to build a classifier of odd versus even digits, or maybe you want to have a classifier of, something else that you're trying to predict. So you're trying to predict multiple things. And again, the setting is that all of it comes from this distribution. Right? At test time, same setup. You have X, you have multiple tasks that you're trying to predict, and it comes from the same distribution. So for example, object recognition images with multiple objects. I show you an object, and I need to recognize there is there's a bicycle, there's a person, there's a table, and there's a cup. So you're trying to predict multiple things at the same time. This would be an example of multitask learning. So how would you set up a multitask learning system? This is how you would do it. You have some input, you pass it through the neural network, and then you have multiple outputs. Right? You're trying to predict Y1, Y2, Y3. So you basically have multiple tasks when you're predicting multiple outputs. And you typically average losses with respect to all of these tasks. This is most commonly used multitask setting. There is something that's called structured output prediction, which is a training time. You have the data, but Y is a data of arbitrary structure. So for example, it could be a vector, it could be a sequence, it could be a graph. For example, if you're interested in doing machine translation, your output is not a class, but it's a sentence, right? Or if you try to do speech recognition, again, your output is not just a single piece, but it's, it could be a transcription. At the test time, again, same setting. Both of them come from the same distribution, right? So it's not like I'm training the model to train, on French to English, and then at test time I'm saying, like, how do you translate from French to Spanish, right? That wouldn't work. So for example, and there's another example I'll show you later, image caption generation. Given an image, I want to generate a sentence describing what's going on in the image. So again, this is an example of a structured output because your output carries a specific structure. One-shot learning, and I'll finish off almost here. One-shot learning is that at training time, you have the data, and you have both inputs and outputs. But at test time, I give you inputs and data, but now I have M additional classes, okay? So instead of having the C classes, I have M additional classes, and I only have a single labeled example from each of the M new classes. The question is, can you now classify these new classes? So this is a setting typically that people would call one-shot recognition, right? Because you only get to see one labeled example of a class. So recognizing a person based on a single picture of him or her, right? If I've never seen a picture of you before, can I recognize you just based on one example, one image? Here's one example that I just wanted to show you. It's kind of fun to look at. Can you do one-shot recognition? Suppose I show you that this is the image of a Zark. How many of you have seen these kinds of characters? Any? I mean, there's kind of like an international. Okay, 1, 2, 3, 4. Okay, good. So you guys keep quiet. For those of you who haven't seen these digits of these handwritten characters before, how many of you think this is an image of a Zark? Yeah. What about this one? How about this one? Yeah, so you see, you can solve it based on just a single example. And you're using some prior knowledge about, handwritten characters and what you've seen before. There's another example of it, like first time you see Segway, you can pretty much recognize it from other Segways, right? It doesn't you're somehow able to parse it and be able to recognize what this is. So how can you learn a novel concept, which is high-dimensional statistical object, from a few examples? Is a big area of research. Right? People can do it very quickly, perhaps relying on some background knowledge. Existing deep learning models can't. You need to have lots and lots of examples in order to classify these examples. And so again, this is an example of supervised learning where I show you and I'm testing you. And this is an example of, I can give you lots of images and I can give you lots of classes. The question is, can you quickly learn from all this background knowledge what this is? So it's a very cool area of research in computer vision, perception, language understanding, and so forth. The last thing I want to point out is, this is an example. This was done by Brandon Lake at MIT. He's built this model, this generative model of characters. Based on one example, his model would generate characters based on a single example, and then he would ask Mechanical Turkers to generate the same example. And the question is, would machines be different from humans? So if you look at these examples, how many of you think that images on the left were generated by humans? And images on the right were generated by machine? A few. What about the other way around? Also a few. Good. I don't know which one was generated by which, because I think it's somewhere in the paper where he included, but when he gave me the slides, I have no idea which one is generated by machine or by human. But you can actually see that it does pretty well in this very much constrained set of generating these handwritten characters. Let me just stop here. I'm not going to cover zero-shot learning, but let me stop here. And so in the next class, we're going to start looking at convolutional neural networks.